Okay, let's move on with the energy concept. Last time we were solving some problems in energy conservation. So far we have seen all the works in our problems done by constant forces, okay? And by constant forces and some certain paths, but we know that forces may change during the course of application. So first, let's analyze the work done by a constant force on a force versus position graph. Okay, if you have an object and a constant force is applied for some path, for some distance, this red line shows the constant force and the horizontal axis is the position of the object. So if you want to find the work done by this force between the positions x2 and x1, what you do is you multiply F by this value by the distance, the difference between x2 and x1. But if you look at this graph carefully, this is nothing but the area between the force line and the position line, the x-axis, okay? So if you multiply the force by d, this is nothing but the area of this rectangle, okay? And size of the rectangle is the f in the vertical direction, and d is the horizontal direction. So this is the work, and the work in force position graphs is nothing but the area under the curve, under the force curve. So having realized this, we can say that if you have a variable force, if the force is changing during the course of action, like here, you may have a force, but when the object moving from xi to x final, the force is changing. Okay, it's not a constant anymore. Again, this time, if you want to calculate the work done is nothing but the area under this curve, under the force curve. And probably you have seen this in your calculus classes. If you want to find the area between a curve, a function, a graph, and the x-axis, what you do is you take an integral, right? And let me write down this integral. For this case, if fx is a function of x, okay, then this area between xi and x final is nothing but the area is equal to this integral from xi, the initial position, to x final, fx dx, right? Probably you have done this many times in your calculus courses, and finding the work done by a variable force is nothing but the application of this concept in calculus, okay? You just take the force times dx integral from initial position to the final position. As an example, let's do this for the spring force. If you have an object and if you pull an object which is attached to the spring, then this applied force must at least be equal to the spring force, right? K times x. And if you move this object from an initial position xi is equal to 0 to a final position, you must apply at least k times x force, right? When you pull it, during the course of pulling, the application force must increase, right? Because the spring force is increasing when you extend the end point of the spring. So just apply this f dx, the force times dx, to the integral. If you put fx instead of fx, this k times x, which is the spring constant, spring force. And if you take, let's say, from the equilibrium position to a final position, the equilibrium position is always taken in the springs as 0, because there is no force on them. And to x, just take this integral, what you find is 1/2 kx squared. So you see that the spring potential energy, in fact, is derived from this integral, right? I have given this spring potential energy initially last time without thinking of this varying forces taking the integral. Just I have given the formula from straight, but in fact this is derived from this integral, okay? And if you, of course, draw a force versus x graph for this process of pulling an object, 1.1 end is attached to the spring, will give you a straight line force, okay? It's a straight line force, and what you do, in fact, during this pulling is you calculate, to find the work, the area of this right triangle. And as you see, this straight line, the slope of the straight line gives you the spring constant. For those of you who have done this experiment today, in fact, calculated this spring constant, okay, by attaching a mass to the end of a spring and observing the spring versus x graph on the lab quest. You have the lab quest. So they just curve it to a straight line graph, and the lab quest, you see, can easily calculate these slopes. So experimentally, you will do this slope calculation in the lab to find the spring constant of any spring. Okay. So let's focus on an example. Probably you will have this kind of questions in your quizzes and also maybe in your final. You will be given a force versus x diagram graph like this, and you will be asked to find the work done by this force for some certain intervals of position. In this question, the force versus x graph is given. Force is in terms of newtons and x is in terms of meters, so that the work is in joules. So first, calculate the work done by this force, varying force, between x is equal to 0 and x is equal to 5, the first part. So what you do is, in fact, you calculate the area of this right triangle, this section, okay? So it's nothing but 1/2, 3 times 5 meters, because the height of the triangle is 3, okay? And one of the sides is 5, so I multiply this and take the half. 7.5 joules for the first part. And second part, what is the work done by this force from x is equal to 5 to x is equal to 10. It's a rectangle, just multiply 3 by 5, 15 joules. And the last time you will calculate the work from x is equal to 10 to 15. And the last question is, what is the total work? Total work is the total area under this curve. It's not a curve, in fact. This section is just a straight line. This is a constant, and again, you have a straight decreasing force, straight line. So you'll calculate add all the areas to find the total work done by this varying force from x is equal to 0 to x is equal to 15 meters. So very easy. Next example is a little might seem complicated to you, but nothing to worry about it, because we will use the force, the work integral work formula. You are given the force as a function of x, you see, and in fact the force is given in here as a vector, not a scalar, so you have to be careful in here. The force is given, the x component is 2x, and the y component is constant, 3 newtons. And the question is, what is the work done by this force from moving an object the vector position, the initial position vector 2 meters in x and 3 meters in y, to the final position minus 4 meters in x and minus 3 meters in y. So the formula that you have to use in this problem is this integral. But the integrand this time is not just fx times dx, but it is a dot product. The force vector dot dr. Okay. Remember, this was just in one dimension, f times dx. But this time, since you are given the vectors, you will calculate first this. But what about here dr? dr is the incremental position change in the xy coordinate system. And probably you have seen this before. dr is a vector, and in fact its components are nothing but dx and dy. But dx, its component in the x direction, and dy, its component in the y direction. And the force has fx and fy components. If you make a dot product of these two vectors, you will just multiply the x component of the force by dx plus, and multiply the y component of the force, fy, with dy. So your integral is, this time, is two different integrals, right? One is in x and the other is in y. What about the limits of the integration? For the x one, the limits is the x component of the initial position, which is 2 meters, and the x component of the final position, which is -4. Okay. For the second limits, since it's in y, the first component will be the first component of the position in the y direction, 3, and the second y component of the final position, which is -3. So when you do this multiplication, fx dx, fx is 2x dx is the first integral from 2 to -4, and fy dy is 3, it's constant, 3 dy, and from 3 to -3. So it's easy to take these integrals. You calculate the integrals from the initial and final points, then you find the work done by this force as -6 joules. You will also have these kind of questions, okay? So you have to know how to dot product these two vectors, f and dr, and find the limits of the integration. The limits of the integration is concerning the x components of the final and initial position vectors, and the y components of the final and initial position vectors. Any questions with this? Okay. So the last topic in the energy concept is the relationship between the conservative forces and potential energy. For this, I will give an example. Start with an example, which is not on this slide. Remember, what was the potential energy of an object which is at a height h on the surface of Earth? It is mg times h, right? But if you, instead of h, you put y, because the distance in the vertical direction, generally the potential energy on the surface of Earth is mgy. And it depends exactly on the mass of the object and the gravitational constant g. What about the force on the object, the gravitational force on the object? It is -mg, right? And I can write this -mg as a derivative of the potential function. The potential function u for the gravitational potential, it is mg y, right? And the force on the object that creates this potential is -mg, right? Its weight. You observe that F can be written as minus du divided by dy, a derivative of the potential function with respect to y, and multiply by minus. Okay? So this observation is true for all conservative forces. Okay? For all forces that the energy is conserved. And it is the same with the spring potential energy. Remember, the spring potential energy is 1/2 kx squared, and the spring force that creates this potential energy is minus kx. But if you take this potential with respect to x and multiply by -1, you will obtain the spring force. So as you see, for conservative forces, the potentials and the forces are related to each other by a derivative. Okay, the forces are always can be calculated if the potential is a potential of a conservative force. If you are given a potential function, you can always find the force on the object. Okay. So, for example, the first graph showing you the potential energy of a spring, it is 1/2 kx squared. If you draw the graph with respect to position, okay, it is just a parabola. The minimum point passes from the origin, and this is the potential function. And from this potential function, you can easily find the force graph, right? The force graph. The force in everywhere at any point will be minus kx, and the force associated with this will be like a graph like this, right? This is the force, and this is x. So once you are given the potential function as a function of position x, you can easily calculate the force at every point. We have, once you're working with the potentials as a graph, as a function of position, you observe an interesting thing, that what you see, for example, the potential of a spring, 1/2 kx squared, you focus on this point, okay? If you move an object which is attached to a string a little bit further in the positive x direction, it will come to this point. It will eventually passes from the origin, right? Because if you pull it and release it, because of the restoring force by the spring, it will pull it back towards the origin, okay? And the object will, in fact, go back and forth around this x is equal to 0 point origin. So if somehow an object has a potential, and if the object, if you slightly move it and release it, moves around a specific point, that point is called the equilibrium point. Okay? In our case, x is equal to 0 position is the equilibrium point of a spring. Well, x is equal to 0 is the relaxed length of the spring. Okay? So this kind of equilibrium point, for the case of spring, this potential is a stable equilibrium point. Okay? We have an equilibrium point, and you also observe that at this point, the derivative of u, the potential, is equal to 0 at this point. Because if you draw a tangent line right at this point, tangent to the 1/2 kx squared, this line is just a parallel line, and the slope of this line is 0. So we define the equilibrium points once you are given a graph of potential with respect to x. We define the equilibrium point as the point where the graph has 0 slope. This is also the case on the right hand side. You see, we have another potential. Let's say this potential is minus y squared plus some constant h. This defines the potential of an object over the top of a hill, that the hill has a shape of parabola. Okay? If the object moves on the surface of this hill, that the hill has a shape of parabola, this completely defines its gravitational potential, minus y squared plus h. You may observe the same thing, right? Y is equal to 0 at the top point. If you draw a tangent line at this point to this curve, the tangent line right at this point will be a tangent line, and tangent line has 0 slope. So you can say this top position is an equilibrium point of the object on this hill. Okay? But is this a stable equilibrium point? If you move the object a little bit from this point, will the object comes to the original point by itself? No. It will go in the either in the positive y direction, and it will never go back to the same position again with the help of the force that created this potential. Or if you move it a little bit to the left hand side, it will go down and it will never go back to the top position by the force that created this potential. Okay? So this kind of equilibrium point is called unstable equilibrium point, because the object is standing there not stable. It's unstable. If even little push will not bring the object back to its original position. So there are two kinds of equilibrium points. One is stable, the other is unstable. We can decide mathematically the type of the equilibrium point, whether it's stable or unstable. You know now how to find the equilibrium point of a given potential. Just take the derivative of the potential and equate it to 0 and solve for x. That x position will be the equilibrium point. If we take the potential function, the derivative of the potential function twice, and if you observe its sign, either positive or negative, if it is positive, the point is stable equilibrium point. If it is negative, the point is an unstable equilibrium point. Let's see this. The first derivative of the potential 1/2 kx square at here 1/2 2 times well, if you take the derivative of this, it's just kx, right? If you take the derivative, it's kx, and kx at the origin is 0. So that's is equal to 0 is an equilibrium point. Is it a stable equilibrium point? Take the derivative twice. If you take this 1/2 kx square twice derivative with respect to x, it is k. And spring constant is always a positive quantity. So second derivative of u at x is equal to 0 is k, and it is positive. That means this point is stable equilibrium point. Do this with this example, minus y squared plus h. Take the derivative once, it is minus 2y. At y is equal to 0, it is 0. So y is equal to 0 is an equilibrium point. You take the derivative twice. If you take the derivative twice of this function with respect to y, you find minus 2. It is a minus quantity, so it is less than 0. That means u, for this potential, y is equal to 0, is an unstable equilibrium point, because its second derivative is negative. Okay? So you will have also these kind of questions in your quizzes, possibly in your final exam. Well, point, stable equilibrium point. Equilibrium points are classified whether they are stable equilibrium point or unstable equilibrium point. You may have more than one equilibrium point of a given potential. An example you see in here. You might have such a potential curve with respect to x. Okay, let's draw an axis here. So you might tell me which points are equilibrium points. Do we have equilibrium points? How many equilibrium points do we have? Between, let's say, this xi and x final, and we don't know the potential in this direction or this direction. We only concern the potential between these points. So you can easily tell me that the first equilibrium point is this one, right? It is the local minima that you know from calculus, right? It is a local minima. And the next one, you have a local maxima, right? What are local minimum and local maximums? in calculus. If you are given a graph of a function f, the local minimum or local maximum is just the points where this function has a zero slope or zero derivative, right? Obviously, this u function has a zero slope at this point, here and here. Also here, another local minima. So these points, these local minima or maxima points, are the equilibrium points. Which ones? Let's label them A, B, and C. Which ones are stable equilibrium and which ones are unstable equilibrium? A and C are stable equilibrium because they are minimums. And if you take the second time derivative, even you don't know the function analytically, just by looking the graph, you can tell. Okay? The point A and C, for this you can just imagine, suppose this is a hill and you drop a marble or an object. If it is at point A, the marble will go back and forth around this point. So it's stable equilibrium. The similar thing for C. But for B, if you drop a particle on the hill, it will fall down to the left hand or right hand side. So it's not a stable equilibrium. B is unstable equilibrium point. Okay, so final example, that this is an example from your textbook survey. And the potential function is given. You are not given the analytic expression, analytically the dependence of u to x, but you see only the graph. And you have some points on the graph A, B, C, D, and E. The first part of the question determine whether the force, the x component, of course, since the potential is a function of x, the force is a force which is in the x-axis. Okay, so determine whether fx is positive, negative, or zero at these points A, B, C, D, E. Let's think about the force at point A. Do we have a changing force? First of all, does the force change along the axis x? It is changing, obviously, because the potential is changing like curves. It's not a straight line. If it were a straight line, okay, if it were like parts of straight lines, the potential, then the force will be a constant force. But since the potential is a curve, the force is also changing. We can say the force is changing. So what can you tell about the sign of the force at point A? Yes. Is it negative or positive? Negative. Why? How do you find the force at point A? Take the derivative of u. Right, at point A, what is the slope? Well, okay. Since you don't know the rest, okay, the potential function in the negative x direction, if you accept that this point A is a local maximum, then the force is zero, because the tangent line is parallel to the x-axis. I mean, if it's not going like this, but if it's a local maximum, then the force at point A is zero, because the tangent line has a zero slope. But I mean, there is not enough information on that anyway. So you can tell either way, either f is positive or negative. But remember, the force is a negative derivative of u. Okay, the force F is not du or dx, but it's minus du or dx. The minus sign makes a difference. Well, let's concentrate on B. What can you say about the sign of force at point B? Is it positive or negative? Positive. Okay. Well, if you draw a tangent line at this point, the tangent line has a negative slope, right? But the thing is, the force is negative of the slope of u. So you will think in the reverse direction. So the tangent line has a negative slope, but the force is positive. What about C? It's a local minimum. So obviously, the tangent line has a zero slope. So the force at point C is zero. What about D? If you draw a tangent line, it has a positive slope, but the force is negative. Because force is minus d over dx, minus the slope. And point E is a local maxima. The tangent line is zero slope, so the force is zero at point E. Well, the parts B indicate points of stable, unstable, or neutral equilibrium. By the way, I haven't defined the neutral equilibrium point. As I said, if the second time derivative of u is positive or is negative, if it's positive, it's stable. If it's negative, it's unstable. What about if it's zero? If the second time derivative of u is zero, then this equilibrium point is neutral equilibrium point. Okay. We have another possibility. Okay. So what about A? If the potential is going like this, if the potential is going like this, what about the point A? Is it an equilibrium point? Yes. Is it stable or unstable? Unstable. Why? If you put an object in there, a little push, the object will never come back to its equilibrium point anymore. What about B? Obviously, it's not an equilibrium point, right? Because the force is not zero in there. After all, if it's an equilibrium point, the force must be equal to zero. What about C? C is an equilibrium point. Force is zero, but is it stable or unstable? It is stable because it's a local minima. If it's local minima, it's stable. If it's local maxima, it is unstable. So similarly, D is not an equilibrium point, and E is an equilibrium point, but it's unstable equilibrium point. Last example, before I finish this chapter, you are given the potential energy function, but this time the potential energy function depends on both x and y. You have two variables. So obviously your force is a force in two dimensions. It has an x component and a y component. In this case, you will find the the force, x component of the force, by taking the x derivative of the potential function. Okay, minus del u over del x is the x component of your force, and this again a function of x and y. So x component of the force is minus 9x squared y plus 7. It's a function of x and y. Okay, and similarly, if you want to find the y component, then the y component of the force, to find the y component, just take the potential derivative of the potential with respect to y. Okay, and multiply the minus sign. So the y component of the force is minus 3x cubed. The y component of force depends on the x position. This is possible. Okay. So your force in total as a vector is minus 9x squared y plus 7i. This is the x component, and plus minus 3x cubed, and this is the y component. So you might also be given that find the work done by this force moving an object from some initial position Ri to the final position Rf. You will take then the integral of this force with dx and dy. Okay, so that finishes chapter 8, and that's all about I can say about the energy, conservation of energy, potential energy, kinetic energy, and overall the mechanical energy. Okay, for those of you who have done the experiment today, and for those of you who will do today or tomorrow, you are given an object hanged by a spring, and you will analyze the potential energy and kinetic energy conversion. Okay, For those of you who have done the experiment today, you have this kind of curve for the potential energy of the spring. You have like this sinusoidal potential energy for the spring. Let's call this U, and this is Y because the spring is oscillating back and forth in the Y direction. And similarly, on the lab quest, you will also see that the kinetic energy as a function of Y also is changing like this. It will be maximum where the potential energy is minimum, and it will be minimum where the potential energy is maximum. So you see, these points are the same points on Y, but when you see the potential energy stored in the spring is minimum, you will notice that the graph in the lab quest will give you a kinetic energy which is maximum. And in fact, the maximum and minimum, all the maximum points of the potential energy in the spring and kinetic energy should be equal to each other because the energy is conserved. Okay, and in the lab quest you will also be observing the total energy U plus K, and the U plus K is expected to be a straight line because this total energy of the mechanical energy will be conserved. But somehow in lab quest you will notice that the total energy is also oscillating, but oscillations will be less than the potential energy or kinetic energy. Okay, this is because there are some errors in the experimental setup, but you will see on average the total energy will stay constant, but you will see that this total energy not constant, you will see a little decrease. These oscillations will decrease a little bit for those of you who have done the experiment. And for the comment of this decrease in the total energy, that there must be a friction, right? And this friction, in fact, goes to the heat of the spring, because if spring is oscillating back and forth, when you move an object back and forth, it will heat up. That's because of the friction of the molecules in the spring material. So, but it's a slow decrease. Okay, it's because damping is very low. So when you draw your graphs in the Loggerlite program in your computer, you must see this observation. Okay, and you will do a comment on this. The energy is conserved. Where the kinetic energy is maximum, the potential energy must be minimum. At least you should see these. Okay, where the potential energy is minimum, the kinetic energy maximum, or vice versa. Okay, so that's all for today, and we will continue on Tuesday.